Hello students, so last time we have talked about oscillations and we have talked about the laws of oscillations, like what we call uh, simple harmonic motions, those things, and we have seen what are the things are important to study oscillation. Today we will be digging more into this thing. Now, to start with, we will be taking some system like a spring and a mass. We will be taking a system of pendulum to study how the time period we can measure and how like oscillation is linked with all the other parameters. So let us start. At first, let us talk about uh, our spring laws. So we are talking today about simple harmonic motions. So why simple harmonic motion? Because simple harmonic motions are very much easier to calculate. Like we can study about them with ease. Okay. We know that for simple harmonic motion, uh, always the force, restoring force, is towards the equilibrium point. So what is the equilibrium point? When the where the object rests. So let's say we have a spring like this. We have a mass or bob here, and it is resting here. Now if you disturb this object and just pull this object a little bit far away and then you leave it, so what will happen? It will start oscillating like back and forth like that, right? So all the time the restoring force will be towards the equilibrium point. So if this is the equilibrium point O, so when it will be going that side, the restoring force will be towards O always. So we know that F is equal to minus kx in this case. So x is the displacement. So we were using y instead, so I'm writing y here. So y is the displacement from the equilibrium point. K is the spring constant, which is a property of the spring material itself, and minus because it is always in the decreasing side of y, right? So that means it is towards the equilibrium point. So we have seen that F is equal to minus ky. Now we are going to find a little bit of relation regarding your omega and this what you say k, that is your spring constant. So see, any kind of system which is uh, let's say which is going under this kind of simple harmonic motion or oscillation, we can do a very nice comparison between them and the spring system. Because if we just compare for any kind of system which is like say is oscillating, let's say I'm just giving you one nice example. Let's say you have a bowl and then you have a marble in it and you just left it, so it will just go back and forth, go back and forth. So this thing even you can compare with your spring system. So I know that in this case there is no physical significance of k, but this k is actually playing a nice role to describe the type of oscillation, like what you say, uh, the frequency of oscillations and that these all things. Okay, so this k, you can say that for different oscillation, this k plays a very vital role here. Okay, now we know that force is mass into acceleration, so that is equal to ky, right? Now one more thing we know, that this acceleration, what we can write, we know that for any kind of oscillation we can also compare these systems with our uniform circular motion as I have said you earlier in the last class, that uniform circular motion is a nice example of simple harmonic motion, because it covers, it rotates again and again throughout the same path. So it retraces the same path again and again in a fixed time. So t is the time period which is required for a complete oscillation. So all the time it completes the oscillation in t time only. So that means we can also compare the spring system with our circular motion itself. Now for our circular motion, we know that the acceleration is uh, what you that is your omega square r, right? uh, I think you remember this thing, that is v square by r, right? Acceleration we were talking about, centripetal acceleration. So for this kind of rotation we can write that a is equal to omega square r. So if we compare this system with our spring system, okay, so what we are actually doing, we know that for spring system no such things are there, like centripetal force is not here. There is no such concept here. But what we are doing, we are trying to compare uh, this circular motion with our spring system. So we are taking help of that concept here. So if we just compare them, so we can, because in both cases the system is retracing the path again and again in the same time. So if we just compare, so I can write, instead of this a, I can write that this is m omega square r is equal to minus k y. So yeah, so this r, in this case displacement is y, so instead of r I will write here y, because I'm comparing these things to here, but here y is playing the role of r. So this is the scenario. So from here what I can write, after comparing the two things, after cancelling out, I can write that omega is equal to, now this minus sign you can remove here, because this minus sign actually signifies only the direction, but I am only concerned about uh, our what you say, omega only. So that's why I can just simply take that thing out. So one more thing you can see here, omega then will be equal to root over k by m. So see what we have done here, we have taken a system like a spring system. We have compared the spring system with uniform circular motion. That's why instead of this acceleration here, we have used that acceleration which applies for uniform circular motion. And then we have compared this with our spring constant. So we have gotten this one, that is omega is equal to root over k by m. Now what is my k? Now see, in this case spring, in case of the spring system, this k is spring constant. But in other system, wherever we are going to use this equation, in other such system, k will play a role for our restoring force. So that means that k will play a role that with certain amount of displacement, how much my restoring force is effective, that will be decided by the k itself. So this k will be not spring constant, will not be called as spring constant for all those other cases, but that will be a coefficient, and you can also say that, yeah, that is a restoring constant, you can say. Okay, just to make you remind that when there is no such spring or something, but still we are writing that formula. So K is there something which is like a very which is a very effective way to understand how much the restoring force is effective. Okay, so this is the relation between your omega and the restoring facility that we have, which creates the oscillation actually. Okay, now we are talking about the energy of this kind of systems. So let us talk about the energies. So energy of SHM, simple harmonic motions. Now we have seen that to describe simple harmonic motion, the displacement of that object. So again, I'm taking the help of the most simplest thing, that is the spring one. So this is the equilibrium position. So it will go till here, and then again it will go till here. So from A to B, it is oscillating, and O is the equilibrium point. It is coming to A and then going to O and then going to B and then coming to A. Like this will go back and forth. So let's say this small a is the amplitude. Now what is amplitude? Amplitude is the maximum extent, okay, or you can say the maximum displacement that the bob can cover. So if this is the scenario, so for any certain time t, we can write the displacement, that is our a, that is the amplitude, sine omega t, that we have seen in our last class. Now if this is the situation, we can also find the velocity, because we know the displacement will time. So I can see here that y, that means the displacement from the equilibrium point. So let's say the bob is here at y distance. So I'm talking about that. So if say the displacement is dependent on t, so if I just derivate, if I just differentiate, okay, if I just differentiate with respect to time, I will get dy dt is equal to minus a omega, sorry, the minus will not come, yeah, so a omega, because omega will come out, cos omega t, right? So that is my velocity, because I know that displacement by time is the velocity. So what will be the kinetic energy? Let us find out. So the kinetic energy here will be half m v square. So that is half m, and instead of v square I can write a square omega square cos square omega t, right? Even I know one more thing, that whenever this displacement will be there, that is whenever the bob will come to that place, what will happen? My spring will be elongated. That means some work has been done on the spring, and that will be stored as potential energy in the spring. So we have seen in the kinematics classes or mechanics classes that the potential energy for the spring is half k x square, and we have derived also that thing. So where this x, instead of this x we will be writing y, because we have taken y as the displacement. So that will be half k, and then instead of y, what we are going to write? We are going to write this thing, that is a square sine square omega t. Now we are going to use that our formula, that is omega is, or you can say omega square is k by m. So we know that k is equal to omega square m, so I can just write that thing here. So that is half, instead of k I'll write m omega square a square sine square omega t. Now I have my kinetic energy, I have my potential energy. So I know that the total energy of the system of the system will be the uh, summation of potential energy plus kinetic energy. So if I just add them, so that will be half m omega square a square sine square omega t plus half m omega square a square cos square omega t. So if you just take common half m omega square a square, and this part will be sine square omega t plus cos square omega t. So that will be 1. So I will get half m omega square a square. Now again we can use this formula to bring the whole thing. So you can use this formula as well. So for any system, if say something is oscillating, going back and forth, so in that case, if I know the mass, if I know like the omega, so instead of omega I can use that time period also, and if I know the amplitude, that means how far it is going and then coming back, then I can easily find out the energy itself. Now where we use, I will give you one example where we use this thing, like this kind of oscillation where we study. So if you just write this thing in terms of say your time, so what will be the value? That will be half m omega, I will write 2 pi by t, that is 4 pi square by t square a square. So this even you can write if you know the time period. And if you want to bring this formula in the form of k, so instead of omega square you can write half. So I'm using another color so that you can differentiate those formulas. So that will be half m k by m a square. So ultimately this thing will cancel out, and you will get half k a square. So what is the total energy? Is my half k a square. So what is so if I know the k, the value of k itself, if I know somehow experimentally, if I just find it out, and if I know the amplitude, then I can easily find out the total energy of the oscillating system. Now let us find out the time period also. From here even we can find out the time period. So let us find out that. So one more thing I'll just tell you. So we have gotten the total energy. We have seen a very important relationship between our omega and the restoring what you say parameter, that is k. Now just let me write this thing, that is omega is 2 pi by t, that we all know. Also we know that omega square is equal to k by m. So if I just put this value here, so that I will get okay. So one more thing I can do, I can write here that omega is equal to root over k by m. So here I can put 2 pi by t is equal to root over k by m. So from here I can write that my t is equal to, so that will be 2 pi root over m by k. It's a very important formula, not just to remember, but you can realize many things from here. So you can see here that m is upside and k is downside. So more you have restoring factor, so if the value of k is higher, that means the restoring force is higher. That means like what to say, the object which is moving from the equilibrium point will come very like responsively to the equilibrium by the restoring force. So the restoring force is trying to bring that object as fast as possible, because the force is higher, the acceleration will be higher in that case. So that means the time period will be less. So if the k is increasing, that means if you bring a spring which is very hard, so elasticity is very high, let's say, so obviously in that case the time period will be very less. So you will see that it is vibrating very fast, because the time period is very less between the completion of each what is a cycle, or each complete revolution. But in case you have a very thin spring, okay, so in those cases you will see that yeah, my time period is high because the restoring force is very low. Same thing with mass or event. So if the mass is higher, so in those cases the time period will be obviously high. So you can just do the experiment. You can just take a thread right here. You can just take a thread. So this formula is valid for most of the oscillations, simple harmonic oscillations. You take a thread, then you give some load, say 5 gram or so, and then just start the oscillation. You now you can just record the time, that how much it has taken to complete one complete oscillation. Then you increase the load, you increase the mass, and then see what happens. So you can understand that how this formula is uh, authenticate in that case. Okay, so we have seen this this formula, right? We have seen what is the total energy of those system. We have seen the time period, even how to find out. Now one more thing is very important, like where to use these things. Now in case of our space exploration, I'm giving you one example. Now in outside of our solar system there are many clusters of gas and all those things, dust particles. So what happens, how we will understand what kind of material is there? So understanding these materials are very important to understand the origin of our solar system and our cosmos. So what we used to do, we used to measure the radiation, not that radiation, like the reflection, you can say, or the emission of some sort of what you say, spectra. It is called spectra, one kind of light, you can say, from them, and then we analyze them. Now in those cases these oscillations are very important, because most of these dust particles are like dipoles, like they have I'm just giving you, let's say, carbon monoxide. There's some sort of that. So they are something like this kind of molecules. There are complex molecules like PAH, you can search in the internet, but polyhydro like something like polyaromatic hydrocarbons. So now in these cases what they used to do, they used to vibrate. So these molecules vibrate, like oscillate back and forth. So they just oscillate back and forth. Also they oscillate in these directions. Okay, so when they oscillate, uh, we can measure how much energy they are releasing. Okay, so we can measure, we can analyze this, and then we can uh, just use our those kind of formulas, and then we can even understand what is the expected mass of these things, molecular mass, and then we can like verify which kind of molecules are there. Are they really carbon monoxide or something else? So because mass is here, which is playing an important role in our time period even. So it is not that easy, but I'm just giving you one brief in like application that where we use these things. Okay, so these are the things we use. Okay, so now the last part is there of oscillation is the some kind of damped oscillation and forced oscillation. So what is damped? See, in this thing, that is the simple harmonic motion, I have said that the simple harmonic motion is called simple because it is very easier for us to analyze. Now in simple harmonic motion, the time period is always same. That means when it completes one full oscillation, the time period is same. But do you really see this in our natural phenomena? If you just keep a thread and hold a thread and then put a stone and then just drop it, like just leave it, what will happen? It will oscillate, but the oscillation will stop after some time, right? So if you have just something like this and you just oscillate, so what will happen? The oscillation will slow down after some time and then it will stop sometime, right? So that means the displacement which I have drawn before like this will not be like this but something like this. Okay, so that means the displacement will slow down, like displacement will decrease gradually and gradually. So this type of oscillations are called damped oscillations. So there are certain kind of damped oscillations, like critically damped oscillation, under damped oscillation, and like something is there which is oscillatory oscillation, like something like a pendulum, what I have said you, over damped, I think, yeah. So something is called critically damped oscillation, something is called under damped oscillation, and something is called over damped oscillation, something like that. But that is not in your syllabus. Just know that, yeah, damped oscillation means the amplitude of the oscillation will decrease gradually. So in some cases it decreases uh, exponentially, like if you have a glycerin tub and then in the glycerin if you just drop a pendulum like here, just drop it, what will happen? It will not go after equilibrium point, it will just stop here like this and slow down. So in this case the oscillation is like exponential, some kind of. So these are called critically damped oscillation. So these are called damped oscillation. Now something is there which is called uh, your forced oscillation. Now what is forced oscillation? Forced oscillation is very simple that you can do in your daily life. You can just uh, hold a thread in your hand. You can just put a stone out there. You just hold the thread out here, and then what you have to do? You just have to move the stone. So what you are doing? You are inducing the oscillation, right? So you are actually oscillating your finger even, and that oscillation is inducing the oscillation of the stone also. So these kind of oscillations are called forced oscillation. So there are so many calculations in your NCERT books which you don't need actually, but you can just read out little bit in order to understand that what is the thing actually. So this is it for today, and in our online classes we will be talking about a little bit hard things to finish this chapter and go for our waves chapter. So till then, bye bye, and what to say, stay safe.